in today's class we are going to look at the linearity and noise of the Gilbert mixers. And this is probably the only mixer for which we will see, because it's the most commonly used mixer. Okay. So first let's look at linearity. So there are two portions. So one is the transconductor, the other is the switching portion. Okay. So let's look at the transconductor first. So what do we know about the transconductor? Of course, we looked at ways to linearize the transconductor a bit more in last class. But let's say you want to use the simplest transconductor. You have area limitations, area limitations, power limitations, and so on. Okay. So and you can't use inductors. You have headroom limitations. You can't use resistors. So if you just have a simple GM stage, what can you do to improve the linearity? We know that increasing the current, increasing the overdrive, right? So that is the foolproof way of improving linearity. Okay, so that is something you can do definitely. But the thing to keep in mind is that, so let's say, okay, so you can do two things. One thing is, so increase the current, but of course you have a power limitation. So let's say you hit that point. The next thing you can do is start decreasing the size of the transistor to increase the V overdrive. Okay, but then what happens is, if you do that, your GM falls and your conversion gain will fall, your noise level will get worse. So that is one fundamental trade-off you have to remember. Okay. Okay, that is for the transconductor. Okay, how about the switch? So let's look at, actually I'll go to the next page. So to look at the switch nonlinearity, you have to look at the capacitances in the circuit. So let's say this is the tail current IT. I1 and I2 are the output currents. Okay, so let's assume that, so this is M1, M2. Let's assume that at that time when we start to analyze, the VLO plus has a rising edge, and at the same time VLO minus has a falling edge. Okay, so these two devices M1 and M2 have capacitances CGS1 and CGS2. Okay. So what is happening to M1? M1 is turning off and M2 is M1 is turning on and M2 is turning off. Okay. What is CGS1? 2/3 WL Cox. Okay, because it's turned on. What is CGS2? You will have only the overlap capacitance. Okay. Is that clear? Okay. So what happens to your, so let's call these two currents. So what's going to happen? Because you have a capacitance and you have a voltage transient, you're going to have a current through the capacitance. Okay. So let's look at what the current looks like. Okay. So we're going to call that IP1 and this as IP2. What do you already know? You know that CGS1 is not CGS2. which means IP1 is definitely not equal to IP2. So next let's call the intermediate node, the common source node, as node X. Let's do a KCL at node X. Okay. So the currents coming in are I1 plus IP1. The currents going out IT plus I2 plus IP2. Okay. So now we can do one thing, because M2 is turned off, we can approximate, I2 will be 0 because M2 is turned off. Okay. And what we are also going to assume is, actually let's rewrite this a little bit differently, then we can see what it looks like. I1 is IT plus IP2 minus IP1. Okay. What we are also going to assume is, because CGS2 is much smaller than CGS1, we are going to assume that IP2 is also very small, almost 0. Okay. So okay, what is IP1? Sorry, what is, why is? Because we are assuming that, because remember that CGS2 is very small. Okay, so the change in voltage across each is the same, but the capacitance is very small, therefore you can assume that the current is very small. Okay, because it's just the overlap capacitance. Compared to IP1, it's, so what we are actually doing is neglecting IP2 with respect to IP1. Okay, not randomly neglecting IP2. Okay, what is this current? CGS1 times T of okay, so this is called the displacement current. And that is, what is going to happen is, there is a displacement current flowing into the current source, right? Effectively flowing down into that node. M2 is off, it is flowing into the current source. Okay, so what this means is, so effectively your I1 is actually modulated by your LO signal in some sense. Okay, and what that means is, depending on your LO signal, so obviously if your LO signal is very sharp, it has very sharp edges, this is going to be very high, and that means that I1, so what that means is, ideally when the transistor is completely switched, you want I1 to be equal to IT, but what's happening is, during a transition time, your I1 actually becomes less than IT. Okay, and what could happen is, if your LO signal is sharp enough, then your I1 could become so small that your M1 could go out of saturation, or at least it will become more nonlinear for sure. Okay, that much is obvious. And what will the signal at node X look like? That you already know, right? So it's going to have all the even harmonics. It's going to look something like this actually. Okay, ideally you want it to be flat. Okay, if your LO signal was a very small signal, it will just be the bias. Okay, it will be input bias minus VGS of the input transistors. But that is just a DC. If you have a larger signal at the LO, in this case we do, then what happens is, you will have all the even harmonics coming in at the common node. Okay, it looks something like this. Okay. What else do we know? We also assume that the switch is switching immediately and very fast. Okay, what do you need for that? So let's consider this guy. Okay, so we assume VLO is large so that it will switch immediately, and it's going to be a function of your transistor over this thing, right, VDSAT. So what that means is your switching speed, if I can call it that, is proportional to your, is actually, let me say, not directly proportional, depends on VLO to VDSAT ratio. Okay, so if your VDSAT is small and VLO is large, that is the ideal condition you want, because the transistor will switch very fast, the differential pair. Okay, but the one thing to remember, you always have some parasitic capacitance at this common node. Okay, so what happens is, so your lower overdrive, you can get it in two ways. One way, increase the size of 1 and 2, which means CP increases, right? What happens when CP increases? So what you are trying to do is you are trying to apply the RF signal here. Okay, RF current flows like this. You want it to flow either here or here, but now you are giving it a low impedance path to flow here. Okay, you don't want that. Some of the signal, so your conversion gain will reduce, which means your noise figure will increase. Okay, the other way to do it, decrease IDC. Okay, which means again GM2 or GM1 or GM2 will decrease, your noise figure will increase again. Okay, so that is the fundamental trade-off for your switch size. Okay, the other thing to remember, so as far as linearity analysis is concerned, you want your LO signal to be large and very sharp. Okay, next we are going to look at noise, and what you will find is, as far as noise from the switches is concerned, you want your LO to not be sharp and not be very large. Okay, that's what we'll see. So there is a fundamental trade-off as far as noise and linearity is concerned again. Okay, so let's look at okay, first of all, so you see that we don't spend a lot of time analyzing linearity. Okay, we do some very basic analysis. The reason is, as far as linearity is concerned, so noise is a small signal, you can linearize the circuit, it's very easy to analyze. Linearity is a lot more difficult. Okay, so it is much easier to get the basics, you understand what the mechanisms are, so you understand that there is a trade-off between overdrive voltage and linearity, and you can rely on your simulator as far as linearity is concerned. Okay, that is the idea. That's why we don't spend a lot of time on linearity, and we tend to spend more time on noise, because in many of these systems noise is as critical, if not more critical, than linearity. Okay, so the reference, I'll give you the reference paper for this. There is a very good paper in 2000 by Human Darabi and Asad Abidi at UCLA. It's called Noise in RF CMOS Mixers. Oops. A simple physical model. So it's in the Journal of Solid State Circuits, volume 35, number 1, Jan 2000, pages 15 to 25. Okay, so this is actually a very good paper. It tries to give a physical basis for the model, for the noise in mixers. What we'll try to do is we'll try to cover only some portions of the paper. Obviously we can't cover it's an somewhat advanced level paper, so we can't cover everything, but we'll try to cover the basics. Okay, we'll see what all we can cover in one class. Okay, so what are the different sources of noise? So first of all, let's look at load noise. That's the easiest to consider. Okay, so what did we see? We saw So far we have seen resistive loads. And we have, I'll just put the mixer core here. Okay, so obviously the resistors are going to have their own thermal noise. We already know that, right? Directly at the output. Okay. Okay, and obviously, since you have two resistors, you're going to have 8 kTRL delta F. Okay, because you're looking at the differential. Remember, you're looking at the differential, taking your output across this. Okay. And you don't have any. Okay, most types of resistors don't have any 1 over F noise. Okay, most types. What are the issues with this guy? We discussed this last class. So your gain is proportional to the resistance, the voltage gain, but your headroom is inverse, like is proportional to the negative. It's basically VDD minus ITRL, right? That's the headroom which you're losing. And as you keep increasing the current, as you keep increasing the resistance, the output DC bias keeps dropping. So that's a problem. Okay. So what you can do is you can use PMOS loads. Something like this. What is your output common mode? It's VDD minus. So let's call this. So it's just VDD minus VGS. Right, of these two PMOS transistors. Okay, so let's say even this is not good enough. So the third thing we'll see is with some kind of common mode feedback. Okay, so you can do some kind of common mode feedback to sense the output common mode, set it to a particular point and set the gate bias based on that, and you will definitely need some kind of compensation for this loop. Okay, so you can set your output common mode to be less than or equal to the VDSAT of the PMOSes, so you can get even better in terms of headroom. Okay, so in these two cases, what do you have? You definitely have thermal noise of the PMOSes adding in, that's for sure, and you have flicker noise. Okay. Now thermal noise is definitely going to be important for sure. How about flicker noise? So let's say we are looking at down conversion mixers. Okay, up conversion mixers, we know we have a tuned load. So let's say it's a down conversion mixer. So what's happening is, so let's say we down convert to IF, and if the IF is large enough, you don't worry about flicker noise again. Okay, because the flicker noise is going to be around baseband. Okay. If your IF is small, or let's say you're looking at a homodyne or direct conversion receiver, I think we briefly looked at it last time, right? Where the IF voltage is, the IF frequency is 0. For those receivers, the 1 over f noise will definitely matter. Okay? Yep. So next, let's look at the noise from the GM stage. Again, we'll go back to the single balance mixer. So this is of course V bias plus VRF. Have a VLO here, right? And we know we are replacing these guys by some SFT. So if we actually so this goes back and forth, switches. So you have the transconductor noise and you have GM times Vin, and you know that your IN squared has the drain noise and the 1 over f noise, it has both. Okay, so this switches as SFT. What do we know? We know the signal that is there in the bottom transistor gets multiplied with your SFT, so effectively it gets amplitude modulated. Okay, what you'll see is, and we know that SFT has components at omega LO, 3 omega LO, 5 omega LO and so on. Okay, so let's draw out the spectrum. So what will happen is, because you have multiple, it gets amplitude modulated, what you'll see is you have contribution to the noise at IF from frequencies that are not around RF. Okay, so let's say this is LO. Okay, I'll use a different color to denote the noise floor. This is your noise. Okay, so let's say your desired RF signal is somewhere here. Okay, what are you going to get? So we know the noise in RF, and of course we also know the noise around the image is going to get down converted. Okay, so let's plot the output waveform also, the output spectrum. Okay, so I definitely have noise from omega RF and omega IM. Okay, now remember that the signal in the bottom transistor is getting multiplied by not only omega LO, it's also getting multiplied by 3 omega LO, 5 omega LO and so on. Okay, so what's going to happen is, we use a different color. If you have some noise which is omega IF away from 3 omega LO, okay, that is also going to get down converted to IF, right? So what is 3 omega LO minus, so this frequency is omega IF. Okay, so this component is going to mix with that noise to down convert it to IF. Okay, and same thing with these two guys. Noise from this guy noise from these two guys and noise from these two. Okay. So let's call this GM over delta F. Okay. This is your input noise per spectral density of current. Okay. And this is going to get multiplied by the noise transfer functions of each one of these components. What is that? Of course, you have to multiply by the square of the gain times 1 plus 1/3 squared. So 1/3 is the, remember you have a coefficient for the 3 omega LO. Okay, and the whole thing times 2, because you not only get noise from the RF frequency, you also get it from the image frequencies for each one of these components. So nice. Okay, times 2. Okay. So what is this? It so happens that this guy happens to be pi square over 4. Okay. So this will give you a 4 over pi squared. So that will get cancelled. You have GM squared RL squared over GM, which is GM RL squared. So okay, so that is going to be the noise from your GM stage. Okay, so that is, we looked at thermal noise, right? Let's call this thermal noise. Okay, how about the flicker noise? Okay, so let's say omega LO again. Okay, this is your RF. Let's say close to 0, you're going to have your flicker noise. But much before RF, it goes to 0. So what's going to happen to this flicker noise? That is going to get multiplied with each one of these components, and it's going to get upconverted to higher frequencies. So you're going to get your omega IF, okay, and remember that omega LO times omega DC gives you an LO feed through component, right? Similar to that, what you'll get is you'll get 1 over of noise around each one of these components. Okay, and we know this can be easily filtered out because LO is very far away from IF or baseband. Okay, can be easily filtered out. Okay, so you have very little 1 over of noise. How about the transmitter? This is for the receiver. How about the transmitter? If you have a transmitter, your omega RF is actually omega baseband, right? The input is actually omega baseband, and that is going to get multiplied. So omega baseband is going to coexist with your flicker noise from your GM stage, and that is definitely going to get upconverted to your RF frequencies. So you will have to combat that. If you have a transmit mixer, you will need to use large sizes. That is probably the only way, right? There is no other way. Flicker noise depends only on DC current and large sizes and the size of the transistors. Okay, so if you are going to design a transistor, be careful about flicker noise from the GM stage. So if you have a TX, okay, so the first two are pretty straightforward. Noise from the load and noise from your GM stage are pretty straightforward. Okay, noise from the LO switches little bit more complex. Yes. Of course, sure you can. But the thing is, the the first stage mixer is always going to have flicker noise, right? Your signal always comes at. If you do a digital thing, then you don't have a problem. That's right. If you don't have, then you would worry about your flicker noise or something else in your analog to digital to analog converters. That's probably what you'd worry about. Okay. Or I mean, if it is a low IF, if it is high IF, then you won't worry about IF. I mean, you won't worry about flicker noise. That's for sure. That's right. Okay. So the first thing we'll notice. Actually, let's draw the. Give me a minute. Okay. Okay, so first of all, what happens when one of these transistors, one of the LO transistors is completely switched? So let's say one of them is on, the other is completely off. Okay, so what that means is, the first transistor which is on behaves like a cascode transistor. Okay, and you have analyzed the noise of a cascode before. You know that if you have a cascode structure, the noise from the cascode transistor doesn't matter so much. It's only the noise from the other main transistor, right? So when it's fully on, no noise. So this is because of cascode. And obviously when it's fully off, no noise. Okay. So the only time when you have to worry about the noise is when the LO devices are switching. Okay. So what we'll see is when they are switching, there are two sources of noise. Okay, one of them is called direct noise, which happens inherently due to the switching performance. The other one is indirect noise, which happens to some kind of parasitic capacitances in the circuit. So in today's class, we'll just do the direct noise. I think most probably we won't even get to finish it. We'll continue next class. We'll finish off with indirect noise. Okay. Okay. So what we are going to do is, we are going to replace. So what does it do? So we are going to replace the noise of these two guys as an input referred noise at the gate of one of these devices, and that's perfectly valid for a differential case. Okay, so we are going to call this Vn. Okay, and of course you are going to have Cp here, some parasitic capacitance. Now just remember, we said that when it's on, there is no noise because of cascode. Okay. However, if Cp is large enough, okay, then the noise from the cascode will start to matter. Right? Well, definitely, you remember that, right? The gain, I think you must have studied in your noise analysis. If you have some parasitic capacitance from the common node, from the drain of the first one and the source of that common node, if you have some parasitic capacitance, it will reduce the gain from the input to the output of this thing, right? Even more. So the noise from the cascode will start to matter. Okay, so just remember that the first no noise assumes that the parasitic capacitance is small. Okay, so what does this Vn do? What this Vn does is, so you want the LO signal to switch at a particular instant, a very deterministic instant, but what this Vn does is, it changes your overall VLO plus to VLO minus profile. Okay, so all it does is it changes the switching instant of the two devices. Okay, so let's say this was your LO signal. Let's assume it's sinusoidal for now. Okay, and that is true in most of these cases. And let's say you have some kind of noise. Okay, that's your VN. So what's going to happen if you actually zoom in here? Okay, what you'll see is it's better. So you have the sinusoid, zero crossing of the sinusoid. Okay, and this was one case was so you have this. So let's say this is your VN. Okay, what's going to happen is the zero crossing is going to change by some delta t, right? Is that clear? What is delta t? So let's say the noise has some profile Vn of t over S, where S is the slope of the input waveform. Okay? Is that clear? Okay. So what is your real switching instant is going to look something like this. Man. Okay, so each one of the zero crossings is going to have some what is called jitter or phase noise. Okay, so we're going to have some obviously around here also. So if you're considering at some ith zero crossing, it will be delta Ti, and this will be delta Ti plus 1. So depending on the actual amplitude of Vn at that zero crossing, your delta T's will be different. Okay. So then what do you do? So we are going to write this as the sum of the ideal switching. So let's call this SR of t. Okay, we are going to write SR of t as S of t, which is your ideal switching waveform. Okay, plus minus 1 plus 1 and so on, plus a bunch of pulses, okay, which contribute to the zero crossing change. Okay, use a different color. Okay, and what's going to happen is the sign of these pulses is going to be either plus 1 or minus 1 depending on the actual value of Vn of t at that time. Okay, and the height of these guys is always going to be 2it. Okay, that is the change in current, right? Okay, and this is of course the width of the pulse is going to be delta Ti, right? Okay, so we'll call this the pulse train P of t. Yes. Actually, okay, S of t is actually a signum function, so it is just plus or minus 1. Okay, the what you can do is once you multiply S of t with the current IRF, okay, you are right. So I should be careful about the height of these impulses. You are right, because I can't say anything about the height of these guys because it's still plus or minus 1. You are right. You are right. Okay. Okay. So now we also know that delta t is V1 of t over S. Okay. Then what we are going to do is find the average value of In of t. Okay, over that period. What is this? It's 2 by t, which is the time period, times, okay, we know that the current is changing by 2 it times delta t. Rest of the time is 0. Okay. And one more thing to remember is that the pulse rate of the pulse train is actually 2FLO. Okay, if the input has a frequency, at every 0 crossing you are going to get a noise pulse. Actually, this is TLO, actually by S, Vn over S. Okay. Okay, so actually need to modify this anymore. What do we know about S for a sinusoid signal? So let's say your LO signal is plus or minus sin omega LOT. The differential is of course 2 sin omega LO t. Okay. dVLO by dt is 2VLO omega LO cos omega LOT, and we are interested in the slope at the switching time, right? So this is 1 at the 0 crossing times at n pi. Okay, this happens to be 2VLO omega LO. Okay, this is S. What is S times T? And omega LF TLO is 2 pi. Okay. Then what we are going to do is, you can also, since delta t is very small, okay, because the noise is much smaller than your LO signal, you can also replace it as an impulse train. Okay? And you can think of this impulse train sampling your noise function. Okay, effectively that's what's happening here. Times. Okay, this guy is TLO over 2. Actually, I'll give this capital. And the noise spectrum is going to be for IT over ST times Vn of f. Right? We saw Vn of t. In of t was 4 IT over ST STLO Vn of t, and the noise spectrum is going to look like this. Okay. So what do we know for flicker noise? And we know what else do we know about this? We also know that this Vn of f is going to get repeated every 2 LO, because it's like getting sampled by an impulse train every 2 LO, right? Sorry, every 2 FLO. Okay. So what you're going to see is at the output, you're going to see flicker noise around baseband. So if Vn of f has a flicker noise, I1 of f is going to have a flicker noise. But you also know the same thing is getting. So let's and let's say this is your okay. What you'll see is every 2 FLO you'll see this, the flicker noise of your switches coming in for the output noise spectrum. Is that clear? But the nice thing to note is that at FLO there is no 1 hour of noise. Okay, and if you are interested in some IF frequencies, there is no 1 hour of noise, probably, or very little contribution from the 1 hour of noise if the IF frequency is high enough. Okay. Okay, so we'll continue with thermal noise next class. Okay, we'll see what happens to the thermal noise from the switches, and then we'll look at the indirect noise contributions.